Whenever a thermodynamic system goes through a cycle, it passes through a series of processes and eventually returns to its initial state. Because it comes back to its initial state, all its properties after the completion of the cycle are unchanged, including its internal energy. Let's say, for example, this system goes through a cycle. It first moves from state 1 to state 2, and then state 3, state 4, and eventually comes back to its initial state, state 1. We can write the energy equations for each process. So, from state 1 to 2, Q12 minus W12 equals U2 minus U1. State 2 to 3, Q23 minus W23 equals U3 minus U2. State 3 to 4, Q34 minus W34 equals U4 minus U3. And for state 4 to 1, Q41 minus W41 equals U1 minus U4. If we add up all the energy equations, we get something which looks like this. On the left-hand side, we can write all the heat terms as just a single term which represents their sum. And we can do the same thing for work. On the right-hand side, if we rearrange the terms a certain way, we see that the internal energy terms subtract themselves out and evaluate to 0. This is the first law of thermodynamics, and it states that when a system undergoes a thermodynamic cycle, the net heat supplied to the system from its surroundings is equal to the net work output from the system to its surroundings. We can also write the first law equation as this. The left-hand side is called the cyclic integral of the heat transfer, and it represents the net heat transfer in the cycle. And the right-hand side is called the cyclic integral of the work, and it represents the net work given out during the cycle. So let's solve a few problems that require us to use the first law of thermodynamics. 0.72 kg of a perfect gas occupies 0.18 meters cubed at 120 degrees Celsius and 350 kilonewtons per meter squared. The gas is heated in a rigid vessel to a pressure of 1,750 kilonewton per meter squared, and then expanded reversibly and adiabatically to 125 kilonewton per meter squared, after which it is cooled isothermally to the original condition. 1. Sketch the cycle on a PV diagram. 2. If the specific heat ratio is 1.35, determine the value of each specific heat capacity. And 3. Calculate the net work done and the net heat transfer between the gas and the surroundings in the cycle. We've been told this is a perfect gas. To sketch its PV diagram, we have to consider the state parameters and the type of process in between the states. Initially, the gas has a pressure of 350 kilopascals and a volume of 0.18 meters cubed. Then it is heated in a rigid vessel to a pressure of 1,750 kilopascals. Because the vessel is a rigid vessel, the volume doesn't change, so this process is isochoric. Then, it expands adiabatically to a pressure of 125 kilopascals. We don't know the volume at this state. For an ideal gas, the PV relationship is PV to the power of gamma, the specific heat ratio, is constant. Finally, the gas is cooled isothermally to the initial condition. For an isothermal process, the PV relation for an ideal gas is PV is constant. So we have our PV sketch for the cycle. Now, if the specific heat ratio is 1.35, we can find the specific heat at constant pressure and constant volume. To do this, we'll need the gas constant, R. At state 1, pressure is 350 kilopascals, volume is 0.18 meters cubed, and temperature is 120 degrees Celsius, or 393 Kelvin. We were also given the mass of the gas as 0.72 kilograms. So using the ideal gas equation, PV equals mRT, we can write R as PV divided by MT. And substituting our values, we obtain R as 0.223 kilojoules per kg Kelvin. Now that we know R, we can find our specific heat. If Cp, the specific heat at constant pressure, divided by Cv, the specific heat at constant volume, equals gamma, the specific heat ratio, then Cp equals Cv gamma, and Cp minus Cv equals Cv gamma minus Cv, or Cp minus Cv equals Cv into gamma minus 1. Now, from Cp equals Cv plus R, we know that Cp minus Cv equals R, the gas constant. So Cp minus Cv equals Cv into gamma minus 1 becomes R equals Cv into gamma minus 1. And Cv equals R divided by gamma minus 1. So substituting our values for R and gamma, we can find Cv as 0.637 kilojoules per kg Kelvin. And using Cp equals Cv plus R, we can calculate Cp as 0.86 kilojoules per kg Kelvin. To calculate the work done for each process, for process 1 to 2, the work done is equal to 0 because it is an isochoric process. For process 2 to 3, the work done can be gotten from W23 equals P2V2 minus P3V3 divided by gamma minus 1, which is the work done in an adiabatic process for a perfect gas. We know all the values here except V3. P2V2 to the power of gamma equals P3V3 to the power of gamma. So P2 divided by P3 equals V3 divided by V2 to the power of gamma. Or V3 divided by V2 equals P2 divided by P3 to the power of 1 over gamma. So V3 equals V2 times P2 divided by P3 to the power of 1 over gamma. And from this, we obtain V2 as 1.27 meters cubed. So we can calculate our work done as 446.4 kilojoules. For process 3 to 1, the work done can be obtained using W31 equals P1V1 times the natural logarithm of V1 divided by V2, or P3V3 times the natural logarithm of V1 divided by V3. We're going to use P1V1 times the natural logarithm of V1 divided by V3, and from this we obtain our work done as minus 123.1 kilojoules. The net work done is equal to the sum of the work done from each process. So the net work done is equal to W12 plus W23 plus W31. And this gives us 323.3 kilojoules. To calculate the net heat transfer, we could use the energy equation for each process and calculate the heat transfer for each process. Or we could simply use the first law of thermodynamics. So our net heat transfer to the system is also equal to 323.3 kilojoules. For our final problem, a mass of air undergoes a cyclic process in a cylinder closed by a frictionless leak-proof piston. It consists of 4 processes in sequence as follows. 1. Air initially at a pressure of 100 kilopascals and specific volume 1.75 meters cubed per kg undergoes adiabatic compression to a specific volume of 0.185 meters cubed per kg, and during this process, PV to the power of 1.4 is constant. 2. 950 kilojoules of heat is transferred to the air per unit mass at constant volume, causing its pressure to rise to 2,500 kilopascals. 3. The air undergoes an adiabatic expansion to the initial specific volume, and for this process as well, PV to the power of 1.4 is constant. Finally, 4. Heat is transferred from the air at constant volume, causing the pressure to fall to its initial value. Sketch the cycle on a pressure-specific volume state diagram and evaluate A. The work done during each process, B. The heat transferred from the air during process 4, and C. The change in the internal energy of the air in each process. To sketch our PV diagram, we need to know the pressure and specific volume for each state. At the initial state, the air is at 100 kilopascals and has a specific volume of 1.75 meters cubed per kg. Then it undergoes adiabatic compression according to PV to the power of 1.4 is constant until its specific volume is 0.185 meters cubed per kg. To find its pressure at this state, we can say P1V1 to the power of 1.4 equals P2V2 to the power of 1.4. So P2 equals P1 times V1 divided by V2 to the power of 1.4. And from this, we get P2 as 2,323.9 kilopascals. Next, its pressure rises to 2,500 kilopascals at constant volume due to heat transfer. For the next process, the air expands adiabatically to the initial specific volume. To calculate the pressure, again we use P3V3 to the power of 1.4 equals P4V4 to the power of 1.4. So P4 equals P3 times V3 divided by V4 to the power of 1.4. And this gives us 107.6 kilopascals. To calculate the work done during each process, we have two adiabatic processes and two isobaric processes. For the adiabatic processes, the work done equals P1V1 minus P2V2 divided by 1.4 minus 1, or P1V1 minus P2V2 divided by 0.4. So W12 for process 1 to 2 equals minus 637.3 kilojoules per kg. Remember, we're using specific volume, not actual volume, so our work done is going to be per kilogram. And for process 3 to 4, work done W34 equals P3V3 minus P4V4 divided by 0.4. And this gives us 891.6 kilojoules per kg. For the isobaric processes, work done equals 0. So W23 equals 0 and W41 equals 0. The net work done for the cycle is equal to W12 plus W23 plus W34 plus W41. And this gives us 254.3 kilojoules per kg. To calculate the heat transfer of the air during process 4, for both of the adiabatic processes, the heat transfer is equal to 0. So Q12 equals 0 and Q34 equals 0. For the second process, process 2-3, we were told 950 kilojoules per kg of heat was transferred to the air. So Q23 equals 950 kilojoules per kg. Always keep the sign convention in mind. We're using a positive sign here because heat was transferred to the air. If heat was transferred from the air to the surroundings instead, Q23 would be minus 950 kilojoules. From our first law of thermodynamics, we know that the net heat supplied equals the net work done in a cycle. So the net heat supplied equals 254.3 kilojoules per kg. And the net heat supplied is equal to Q12 plus Q23 plus Q34 plus Q41. The only unknown here is Q41, and that's what we intend to find. So from this, substituting all our values, we obtain Q41 as minus 695.7 kilojoules per kg. Finally, to calculate the change of internal energy in each process, we use the energy balance equation. For process 1 to 2, Q12 minus W12 equals U2 minus U1, which is the change in internal energy. So substituting the values for the heat and the work, we obtain the change in internal energy to be 637.3 kilojoules per kg. And we do the same thing for the other processes. So for process 2 to 3, Q23 minus W23 equals U3 minus U2. And we obtain the change in internal energy as 950 kilojoules per kg. For process 3 to 4, Q34 minus W34 equals U4 minus U3. And the change in internal energy is minus 891.6 kilojoules per kg. And finally, for process 4 to 1, Q41 minus W41 equals U1 minus U4. And the change in internal energy for this process is equal to minus 695.7 kilojoules per kg.